The universe is unimaginably vast, filled with countless stars of all shapes, sizes, and lifespans, from tiny, dim red dwarfs to enormous hypergiants that dwarf entire planetary systems. To understand the scale, we can start on Earth. Even the largest planet in our solar system, Jupiter, is enormous compared to Earth. It is about 11 times wider and 317 times more massive, composed mostly of hydrogen and helium, similar to stars, but far less dense. Jupiter is a gas giant, a planetary body that hints at the materials and processes involved in star formation, but it lacks the mass to ignite nuclear fusion. The bridge between planets like Jupiter and true stars is formed by the so-called brown dwarfs, objects that are sometimes called failed stars. Brown dwarfs have masses between about 13 and 90 Jupiters. They are massive enough to trigger some nuclear reactions, glowing faintly, but not enough to sustain full-fledged hydrogen fusion. Adding more mass to a brown dwarf does not make it larger in size. It becomes denser instead. Only when the mass crosses a critical threshold does the pressure and temperature at the core become sufficient to ignite fusion, and a true star is born. Stars begin their lives on the main sequence, where the delicate balance between gravity pulling inward and energy from nuclear fusion pushing outward maintains stability. Hydrogen in the core fuses into helium, releasing enormous amounts of energy, which manifests as heat and light. Stars that are more massive burn hotter and brighter, but their lives are significantly shorter. Small stars, like red dwarfs, barely a tenth of the sun's mass, burn fuel slowly and can last for tens of billions of years, much longer than the current age of the universe. Our own sun, a medium-sized star, dominates the solar system with 99.86% of its mass, burning hydrogen into helium at a steady rate. More massive stars, such as Sirius, twice the mass of the sun, shine brighter and hotter, but exhaust their fuel more quickly. The largest main sequence stars can have 10 or more times the sun's mass, surface temperatures exceeding 25,000 degrees Celsius, and luminosities tens of thousands of times greater than the sun. But they live only a few million years before exhausting their hydrogen. Interestingly, the most massive stars are not the largest in size. For example, R136A1, the most massive star known, has a mass about 315 times that of the sun, but its radius is only around 30 solar radii. Its extreme mass produces incredible luminosity and temperature, and stellar winds strip it of hundreds of billions of tons of material every second. Because of this, there is a natural limit to how massive a star can become, typically around 150 solar masses at birth. True giants in terms of size are not born massive. They become enormous in their later stages. Once a star exhausts its core hydrogen, the balance between fusion and gravity is disrupted. The core contracts and heats up, while the outer layers expand, forming giant and supergiant stars. For instance, the sun will one day become a red giant, expanding hundreds of times its current size and engulfing the inner planets. Among the most spectacular are hypergiants, rare stars with enormous radii and surface areas capable of radiating incredible amounts of light. Examples include Pistol Star, a blue hypergiant with a radius 300 times the sun's, and Rho Cassiopeiae, a yellow hypergiant about 500 times the sun's radius and 500,000 times brighter. These stars live brief, unstable lives, shedding mass through intense stellar winds, and are so massive that their outer layers are barely held by gravity. The largest star currently known is Stephenson 218, a red hypergiant with an estimated radius of 2,150 times that of the sun. If placed in our solar system, it would extend beyond Saturn's orbit. Its light is nearly 500,000 times that of the sun, and its mass is likely half of what it had when it formed. These stars are so large and distant that measurements come with significant uncertainty. But they represent the extremes of stellar evolution. Hypergiants eventually collapse in spectacular supernovae, scattering heavy elements into space, which then seed new stars and planets, continuing the cosmic cycle of birth, life, and death. The story of stars is also a story of scale. While a red dwarf like the star of Barnard is barely visible without a telescope, a star like Stephenson 218 makes our sun appear tiny, like a mere speck of dust. The sheer size and energy of these stars challenge human comprehension. Light would take almost 9 hours to travel around Stephenson 218, and a spacecraft flying at the speed of the fastest planes on Earth would take centuries to orbit it. Yet despite their enormity, these stars are fleeting on cosmic timescales, living millions of years instead of billions, burning furiously, and then collapsing to enrich the universe with heavier elements. Every generation of stars contributes to the next, creating a continuous cycle in which the universe evolves, shines, and grows ever more complex. From the small red dwarfs to the titanic hypergiants, the diversity of stars illustrates both the incredible scale of the cosmos and the remarkable processes that govern its life, energy, and matter. The universe is vast, mysterious, and filled with wonders that continually push the boundaries of human imagination, reminding us how small our world is and how extraordinary the cosmos truly is.